we can start. So I will introduce you briefly and then, okay. So welcome everyone to today's seminar, Cyber Physical Systems. It is my pleasure to introduce you to Dr. and Professor Tao Dang. So Tao obtained the master's degree, diplôme d'ingénieur, and the PhD from the Institut National Polytechnique de Grenoble. And she was also a postdoctoral researcher at UPenn in Philadelphia, and then became a researcher at the CNRS, the French National Center for Scientific Research, and a research director there in 2014. And she's also a permanent member of one of the most prominent European laboratories in verification, formal methods of cyber physical systems as well, with lots of connections with companies that are adopting the techniques developed in this lab. So the domain of expertise, the interests of Tao are hybrid systems, formal verification and test generation for hybrid systems, with application to cyber physical systems and also systems biology. So we are very much looking forward to her talk. Welcome, Tao, on the stage today.
Thank you very much for the introduction. So the topic of my talk today is about falsification cyber systems, especially with spaces, combining two methods, sampling and optimization. My collaborators, Benoît Barbeau from University Paris-Est, Nicolas Basset from Verimar, so my colleague in Grenoble, Alexandre Donzé, so he's now created and worked for his startup, Decipher, in France. So the startup was created at Berkeley, in fact, when he was postdoc there. And James Kapinski and Tom Yamaguchi from Toyota. James now, he left Toyota and moved to Amazon. Yes, yeah, I have some. So I think that for this seminar, I would not need to motivate the research on cyber physical systems, but I would just want to show some nice pictures of my favorite applications from very daily applications like the water boiler. But you will need to have a good boiling quality if you want to have a good tea, and also to more complicated things like pacemakers, and very popular, of course, applications on autonomous vehicles. So in terms of the falsification problem or validation problem, I would point out some characteristics of cyber physical system that would make the problem difficult. So first of all, you have in cyber physical system components of different types, of different dynamics. So for the physical components, very often you have continuous dynamics described by differential equations, and often you also have algebraic equations, constraints in there. And for the cyber part, you could describe using discrete dynamics, automata, but very often you would have some complex switching conditions and guarded transitions, like if you use automata. So furthermore, between these components of different types, you have very complex interactions, and they are not fully understood because continuous dynamics and discrete dynamics are studied in different communities, like in control theory for the continuous part and in computer science community for the discrete parts. And also, in addition to the interaction between the components, you have the interaction with the environment. where the cyber-physical operates. So we could say that for the analysis of such system, continuous dynamics are difficult to analyze. You have no linear dynamics. And for the discrete part, you can use some advanced like verification methods for discrete systems, but still you will have a very large state space, and also the interaction between the discrete and continuous are difficult to model rigorously, formally. So very often for the industrial cyber-physical system, we will need to use, we would say, lightweight verification. So you have formal verification, that means that you prove formally the system satisfies some property. Lightweight verification is you would give a less formal guarantee on the correctness of the system, and mainly they are based on testing. And in fact, in industry, they are the only, I could say that they are the only tractable validation techniques that we can use on an industrial scale. So in order to have a CPS validation approach, you would need the following key elements. So first of all, you would need some requirements, and you would like the requirements to be formal. So it's that somehow when you express the requirements, everybody would understand the same thing. So it's you would need some formal language to express the requirements, and also you would need to generate input stimuli or test cases to test your system. And then you would want to have some automated, because the industrial cyber-physical systems are large, so you would not be able to manually generate test cases. So you would like to have some automated test generation algorithms, and they somehow based on some optimization, because the state space of the system is too large. So you would need to optimize, you need to have some criteria for the test generation. So for the first element, formal requirements, in this work, we use signal temporal logic. So it's one of many formalism based on temporal logic for discrete time, like LTL. And signal temporal logic is an extension of the discrete time temporal logics to dense time. So let's see, here is an example that you can specify properties of this kind using STL. So it's like you would like to see that between 1 second and 5 seconds, it's the horizon, part of the horizon, the signal should be between minus 2.5 and 2.5. So you have this zone. So this zone is specified by the time interval of interest, and also the value interval that the system should stay within. So you can specify properties like with the operator, temporal operator, always between 1 and 5, I mean in time horizon, the absolute value should be smaller than 2.5, so in this zone. So you could define a Boolean semantics for this logic. So that means that you have the Boolean satisfaction, true or false. But in order to do optimization, and especially adapted to real valued signals, it's better to have some quantitative satisfaction, and we will have some the quantitative satisfaction meanings that the degree of the robustness of the satisfaction is no longer true or false, but it will be a real value satisfying how far you are from the violation of the properties. So you could see that here. So at this point, the robustness of satisfaction is that you will it's 0.7, because the distance from the signals to the boundary of this satisfaction zone is 0.7. And then you would take the smallest robustness to define the robustness of the whole signal. And now there is another. So in another case, when you have this zone, gray zone satisfaction here, but now the signal is is outside this zone, and the robustness is negative. That means that the signal violates the property, the requirement. So it's now we can see that you have more complex properties with the more complex temporal orders. So, for example, here we have a property which is very common in the signal, especially signals generated by control system. You would want to say something like always when the absolute value of x is beyond 0.5, then after 1 second, the signal should be the absolute value should go into this gray zone and stay there for 1.5 seconds. So it's like a stabilization property. That means that whenever you go out of the neighborhood of the equilibrium, you would want the system to return to the zone near the equilibrium and stay there for at least some time. Okay, so that is then you will need to use two operators, temporal operators, always and eventually. Okay, eventually is to say that you don't specify exactly when the system should return to this neighborhood, but you would require some duration of time that the system should return within this stabilization zone. So it's the same thing. You could define the quantitative satisfaction by the robustness of satisfaction for such properties. And there are algorithms to compute efficiently the robustness of satisfaction of any STL formula. So you can have nested temporal operators, complicated predicates as well. So now we have the requirements, formal requirements. We have a quantitative semantics that we would be able to perform optimization on the robustness of satisfaction. Now we could formulate the requirement falsification problem. So first of all, we would like to, so in the testing problem, we will have the tester that manipulates the input to the system and then observe the output and then check whether or not the system satisfies some properties. The properties will be of the system would be specified using some STM formulas, 5 here in that case, in this case. And very often the system interacting with the environment. So the input to the system represents the environment, and the environment is not anything. It should satisfy some properties as well, some requirements as well. It's then you will have the input signal satisfies also some temporal constraints that we would define with note here psi. So the problem, falsification problem, would be you'd like to find the input signal satisfying some constraints such that under this input signal, the system, the output of the system, or any variables inside the system violates the desired properties specified by phi, the temporal logic formula phi. So now here is one possible solution to this, is that we would use the rejection-based approach. That means that first of all, we would like to generate input signals. So now we would here, for example, you generate the input signals. By the way, do you see my my mouse? Yes, okay. The input signal. But then you need to see whether or not this input signal is valid. That means that it satisfies the constraint sign. So you would define again here the robustness satisfaction, because if it's positive, that means the signal satisfies the constraint. If it's not the case, then you will need to somehow manipulate again these constraints and these signals using the robustness to find the robustness that will, the signal that will satisfy these constraints. Whenever you find a valid input signal, you apply to the system, and then you will check whether or not the output X here satisfies the requirements. And then you loop over this input generation, checking the validity, and then checking the satisfaction of the system. But very often you will be stuck in this loop, because when you have very complex temporal constraints, then you would very often, especially if we have the space of the feasibility of this constraints, the space corresponding to the feasibility, it's very small for the compared to the space that you can manipulate. There's a chance you fall into a feasible input signal is small. So that's why very often you will get into this rejection loop rather than going to the valid to generate valid signal. So here there are two limitations with this simple or simplistic approach. Is that first of all, the constraint inputs here we don't yet mention which constraints we are considering, but we will see that even very simple temporal constraints, common temporal constraints of signals, it's not so easy to express in STL, and furthermore, the simple generation can result in very high rejection rate. So now let's see some examples where the temporal constraints can be difficult to be expressed using STL. So we have the delta sigma modulator, and we would like to consider quasi-periodic inputs. Quasi-periodic inputs means that they're not exactly inputs, periodic. The periods could be within some interval. It's not exactly one single value, but it could be in some interval, small interval. And so the property, very common properties of delta sigma modulator is that it wants the signals, the output of some integrators in the delta sigma would not reach the saturation zone. That means that the integrators are not saturated. So it stays within some interval, and the input is the quasi-periodic. Okay, because you would like because there are there are noises, there are many perturbations from the environment that basically the input signals cannot be perfect. So it's not easy to express quasi-periodic properties using STL. And then another example is a very well-known benchmark in the CPS community. If you have this from Toyota automatic transmission system, and you would like to have the property of the system of the output, is that you will the engine will turn into, or will use the gear 4 only when the speed is high. Okay, it's a very common common sense, easy to understand. And but the input signals, it's in fact it's the throttle or it's and or the braking. So it's the driving behaviors of the driver. So then this is it's not so easy. You will see that to express, because you need to define very large variety of how people drive. Like I would brake very abruptly. I will not accelerate at all, or so it depends also on the condition. If you drive on the highways, or if you drive in the city. So this is also something that we see, that the specification of the system are often easy to express using temporal logic, but other properties related to the signals, then they are harder to express using common formalism from temporal logic. So now let's summarize some points in our approach so far. So first of all, you have some requirements for the performance or for the correctness of the system that can be expressed and manipulated using quantitative semantics of temporal logics. So then you have here some functions, robustness functions, measures the satisfaction level of some temporal logic, signal temporal logic formula. On the output signal, here I mentioned outputs, but you can have also some variables, whatever signals that you can observe, okay, or also related to the input as well. And here is the example of to illustrate the semantics, the robustness, the semantics. And now we have these real valued functions, robustness functions. You could try to do the optimization. That means that we try to find the worst case input signals, that they're functions that will minimize the robustness of the system. Okay, so, and you would like to consider only a class of input signals, functions that satisfy some constraints. Okay, so here we see that you are doing the optimization, an infinite dimensional optimization problems, because you need to deal with the function space now. It's not, it's no longer point space. So another important point, if you want to use optimization for the falsification, is that for the like a real life cyber physical system, is that you will need to deal most of the time with the black box system, because the industrial and cyber physical system, like the moderns using framework like Simulink, for example, state flows or other, you will have a very big model that you don't know exactly the semantics, because you have many components from different parts, different dynamics, and designed by different people. So this input-output function are highly complex in general. And then inside there, you have differential equations, you have automata, you may have lookup tables, you have time delay system. That means that you have here, by the system already, you have something infinite dimension already. And that's why very often you will need to use something called black box optimization. That means that you will not need to have the derivative. You do not need to have an explicit descriptions of the system. You can use the derivative-free optimization methods, of course, with a much less theoretical guarantee on the results than compared to when you have a derivative information. So that is one problem. Another problem is that now we need to deal with the function spaces and signal spaces and constraints, moreover constraints. So then very often for the signals in the cyber physical systems, you will have properties like bounded variabilities, quasi-periodicity, some signal specific properties. And we see that if we don't have a way to deal with those constraints, then you will, and you just do some rejection sampling, then it's not very efficient. And furthermore, when you deal with testing, you would need quantitative guarantees. You will need some guarantees, because you could do a lot of tests, but when you don't find any bug, you cannot conclude. If you don't have any measure to say that what is the portions of the behaviors that I have explored, and then you can, from the tested behaviors, you can deduce something like I already studied well enough my system. Here is the average robustness of my of the satisfaction. So to deal with all those challenges in the falsifications of real life in a cyber physical system, so we proposed the following a solution with the following points. So first of all, in order to specify temporal constraints of the signal spaces, we use time automata instead of using signal temporal logics or other form of temporal logics, because it's the time automata. Well, in general, it's the powerful formalism for specifying signals with time constraints and on the sequences of events. And more importantly, for time automata, we have a way to map a trace of time automata to a point in some unit box here. The unit box here is the, you see that is the ranging from, you have n-dimensional unit box. You will see why in more detail, but basically here, you transform a function space to a point space. So then you can do optimization in a finite dimensional problem. And we can do the uniform sampling as well as low discrepancy sampling. And in fact, uniformity and low discrepancy, you will see later as they are like coverage measure. They will tell you how well the test that we use has explored the state space, the reachable state space of the system. So together with the coverage, we would use some meta-heuristic to solve the optimization problems. Why meta-heuristics here? It's because we do not have the derivative information, so we need to use some heuristics. And meta-heuristic is to say that it's the heuristic based on a little bit on the heuristics, usual heuristics. So now we will have the diagrams of our approach is that you will replace the rejection, like a little bit blinded rejection sampling with the time automata based input signal generator. And then we plug into our previous diagram again to generate signals that by construction satisfies already the constraint. So you don't need to, you will not generate invalid input signals. And then you just need to check the output of the system under the generated inputs, and then check the properties and conclude on the guarantees. So now let me give a very brief overview of time automata. So here I will again use this delta sigma modulator. So in fact, the quasi-periodic input signals to the delta sigma. So you have a signal. So here, and then you have a periodic signals. And of course, at the beginning, you will have some phase and maybe it's uncertain. So you will have a few states in the time automata to describe this part. And then you will enter into the periodic part. And then you will use this loop. Okay, so now just maybe some of you may not be familiar already with the time automata. I will recall. So they are basically automata, but augmented with clocks. So here we have 5 clocks. So one clock is the global clock, okay, that is never reset. It's basically, it measures the horizon of the time, the absolute time. And then the clocks can be reset at the transition. So here, this transition, you reset the clock to x1. The clocks are continuous variables with the slope 1. Okay, so, and then here, you use the clocks to measure, for example, I would like to specify the constraints of the duration of time between any pairs of consecutive events. So that means that whenever I take a transition, it will take between the time 0 to 5, 0 to 4 here. And furthermore, so suppose that when I enter this periodic part, I would like if I take this transition, the next time I take the same transition, I would like the time to be between 8 and 12. So it's exactly here where I specify the uncertainty on the periods of my signal. Okay. So now you have this automaton, and then a trajectory or trace of the this automaton can be specified using time words. So that means that they are sequence of vectors that related to the transition A. Okay, and it could be A, B, C, D here. So it's the action, or we say label or actions, and a time. Okay, so then you have the time words. So here, for example, I start with the state Q0. I go to the Q1. I let so between the Q0 and Q1 is the 2.5 time. Okay, and then the label associated label is B. So again, from here to there, it's 2.5 and then so on. So that means that given a time automaton, if we want to generate time words that satisfy, that is inside the language generated by this automaton, we cannot do just randomly. We need to be careful to generate time words that is recognized by the automaton. So that is in fact exactly our goal here. And moreover, we want to generate traces not recognized or valid, but also in a uniform way. So why we want to use uniform? If you have uniformity, then you can have a lot of guarantees, like in the Monte Carlo guarantees on the confidence intervals, etc. So now, if we want to use uniform random samplings, so basically we will define a map, the map between, so suppose that now I want to generate a time word uniformly, and the time word has n transition. Okay, so then here is the n, because the length of the time word is n. Okay, then I will consider the unit box of the dimension n, and we can define a map from this unit box to the time language of the automaton. So in fact, we try to generate the delays between the actions or the state in the time words. So then you have a vector from inside this unit cube, unit box, and then this corresponds to a time words inside the time language. So now, what is the important property of this map is that if you sample a point inside this unit box uniformly, then the corresponding traces are also uniform within the time language of the automaton. So that means that you reduce the problem of sampling signals uniformly into sample points uniformly. So that is the key points here. So, and also we can replace uniformity using something more deterministic. Is a low discrepancy measure. So now we have the timing in the constraints. You have dealt with the timing constraints in the generation. We need now to add the values constraints. Now suppose that for each, the label associated with the transition, we will associate with the constraints on the values. So then again, we will have not only one vector of parameters specifying the timing constraints, you have another parameter specifying the value constraints. And again, we can do the uniform sampling over the constraints of the predicate. So if in the case of the interval predicates, like here in the case that if you have some signal specifying, for example, the speed of the engine, then and if they are simply intervals, then sampling within this interval predicate is very easy. So now let me show how this map, we can just a geometric intuition behind the map between the unit box and the time language. So basically, you have this simple automaton to illustrate. And then, in fact, the corresponding to the each trace of this automaton you have behind the reachable space. The reachable space, in fact, they are time polytopes. So in fact, here, if you go enter this location, you let the time pass, you take the transition labeled with A. So that means, and together with the delay, that means how much time you wait here and then to take the transition. And then you have a variable. So the first delay, and then if you take this transition, you have the second delay. So then the relation between the delay would form a set, reachable set. And basically for the time automata, you will have the set pretty simple in the polytopic forms. And then in order to define a uniform distributions over traces, you define the uniform distributions over the reachable space, which are polytopes for the time automata. Okay, so that means that you see that because the uniforms, to define the uniformity, you would need the notions of volumes. So that's why here you would the problem boils down to compute the volumes of the polytopes generated by time automata. So then you will define this once you have this the time of polytopes, you could define this transformation from the unit box to the polytopes. Here in this case is simply a triangle. And I would just want to mention here that this transformation and these computations of volumes of polytopes, the methods are implemented in the tool worked by my colleague Benoît Marbeau at the University of Paris-Est. So now let us summarize our approach. That means that now we have here the time-based input generator, and then we could use the two tools. The first tool is the word-gen, the tool that I just mentioned, to generate traces of time automata and corresponding input signals. And the second tool is the bridge tool. The bridge tool the goal is to check this. Given input signal, it simulates and then it checks the robustness of the corresponding STL requirements and decides whether or not we detect violations or we detect a satisfaction. So now let me show some example. So here is the example of the driving pattern together with the engine control. So the driver here is this automaton will describe the behaviors of the driver. That means that it can accelerate, it go to the coasting within some time constraints between the actions, and it can brake and then it go to coasting again, it can accelerate. And so this is I think that this automaton is used to describe the driving behaviors, the average driving behaviors within city. So now the word gen will generate uniformly traces of this automaton. Suppose that here we will have here this signal here, the last figure. You have the time words. So it means that here within the first time interval, you will take the first transition. That means entering this S0, because we have here like 5. We go into the 1, 2, 3, 4, 5, 6, depending on the number of transition. And then for the next next step, next step, yes, you will take the first transition. That means here it's the first transition, and then for the second, you take the second transition, and then you jump into this one, here, and you return to the acceleration. So also you have within this is the delay of the transition, specifying the timing, satisfying the timing constraints. And of course, together with this, you will have the constraints on the values, and then you will pick here, for example, the throttle is between 0 and 100, and then you can uniformly randomly pick one value to specify the values of the throttle. So that is the one example. Another example is the, again, we consider this input generation for the delta sigma modulator. You have the same time automaton that we have seen. So if we just randomly choose the signals, then you will see that very quickly the period would not satisfy the constraints. And if we use the time modes, then you will see that, okay, we can generate pretty uniformly. That means well distributed and signals satisfying period constraints. So here is another experiment. That means that we could try to use STL to partially express quasi-periodicity. So this we'll see that, okay, this formula is not exactly quasi-periodicity. It's to say that, okay, whenever you see an up, it's an up, then you will need to see an up again. It's to see that, okay, you are periodic. You see a down, then you will see a down again. And then between the up next, you will need some time. Okay. The up next here is specified that eventually within this time, you will go up again. Yes. So it's very conservative, as mentioned here. And even it's not exactly the property we want to specify. And if we use the rejection based on this property, we will see that we will be able to generate things up to 3 periods. I mean that with reasonable time. But if we use the time automata based approach, then we can generate signals for much larger number of periods and with no time. They're very efficient in terms of computation time. So now that is the first element of our approach. I see my time. Yes, okay. Oh, I think that, okay, so the second point here is the optimization. Okay, so now maybe I will go fast here. It's basically we would need to use the black box optimization. And in our work, we will, because we have the measures that the coverage measure based on the uniformity and low discrepancy in the generations of the input signals, we could use that to improve the black box optimization. So the idea is that the black box optimization, mainly you will have two strategies. The exploitation, that means you try to improve the objective functions. The exploration is you want to explore widely, because in case that you are stuck around some local optima, then you would like to go further, to go away from the local optima. So in order to detect the case of blocking case, we could use the measures of coverage and robustness. Is to say that here, for example, maybe I will go fast. So whenever the blocking situation is that when you see that you do not improve in coverage, you will just going around some area, local area. And the robustness is not improved. That means that probably you are in the near a local optimum. So then in that case, you will need to do the exploration strategy. You will need to sample uniformly or quasi-uniformly over the state space to jump into a more potential space to explore. And yes, so let me go back here to give the two measures, coverage measure that we use. So we use the first is the very simple things, because you know that the time automata language now is mapped into the unit cube. So you just need to define some measure, coverage measure on the unit cube that will correspondingly give you the coverage on the traces of the time automata. So then the first measure is that you cut the state space, the cube, into cells, and then you would count how many points, how many cells that are occupied by the exploration, and then compare to the total number of cells. But of course, this is it's not when you have a lot of cells, then it's not it doesn't correspond exactly to the uniformity. So we have a more theoretical measure, which is the Kolmogorov-Smimov Statistic. So basically, when you transform into the unit box, now you can compare the empirical distribution of a given sample compared to the exact uniform distribution defined exactly by the volumes. The volume here, if you have a point, a box in there, then you simply multiply the coordinates, then it will get you the volumes, and then you can define exactly the uniform distribution. So then you compare the empirical distribution of your sample with the exact distribution, and then you will take the supremum to define this Kolmogorov statistic, Birnov statistic. So yes, so let me show some results. So we applied our approach to a number of case studies. So then we see that, okay, I didn't mention, but basically using the coverage measure and robustness measure, we are able to combine different methods for solving black box optimization as well. And we'll see that if we use this combined metaheuristics, we obtain much better results than just using them alone. Because if you use them alone, you get into the local optima very quickly. And you don't know how to detect, and you just stay there for a long time. So we have some good benchmark results. So conclusion, yes. So here we consider the optimization approach for falsification, and especially combining with the sampling in order to handle temporal constraints in the input signal spaces. And also for the future, we would like to consider different coverage measures, like for example, combinatorial entropy. We would like also to use different algorithms from the communities of black box optimization to improve the sampling efficiency. And we would like to have more complex constraints on the signals, like predicates that combine both values and time, because now it's only separate. You have predicates on the values of the signals and predicates on the times. So yes, I think that I will stop here.
Thank you very much for the great presentation. So let's open the talk to questions. If anybody from the audience want to raise the hand or just write down in the Q&A or the chat, please, very welcome. And otherwise I will ask some questions. So actually, that's very interesting approach to falsification. I was just wondering, for the first right case study or the first approach that you were describing, so how expensive is, for instance, from the specification to build the timed automata, and whether, yeah, you have an estimation of that or strategy that are there for doing this effectively?
Yes, so to build the time automaton specifications, yes, that is so far is still manual. it will need to for the engineer to know the semantics of time automata. But I myself personally, I believe that it's not more complicated than signal temporal logic, like with the nested until or nested eventually.
Right.
Because somehow time automata, beside the timing constraints, you have the automaton structure, which is pretty, then most engineer would be familiar with the automaton structure. So then I think that it could be even more easier for engineers to specify time automata constraints.
And
than
so,
temporal logics.
So in the method, you would have this only for the inputs and still keep
Yes.
the logic for the system behavior and so on.
Yes.
Yeah, and so so indeed, it looks like also in the search and in the optimization, you have these black box methods, and so yeah, probably just a question to elaborate more, right? On there is always this issue in certifications and so on when you want to prove the satisfaction of a property on the confidence that indeed that you give away, especially if you never find a bug. And so you want to say this measure of confidence. So do you think, so far it looks like you have an effective methodology for estimating the space. Do you think it makes sense, or have you tried any probabilistic measure of confidence there? Or can this be translated into some belief into the explorability of the space? Or completeness measure?
Yeah, I think that, okay, so in fact here, our system is the deterministic. We just randomize the search. So if we want, I think that it could be very interesting to consider stochastic system. That means that, so because even here there is no random elements in the dynamics of the system or in the inputs. If we could embed some information, stochastic information into the input signal space or into the dynamics, then we will have, I believe, that more effective way to talk about probabilistic guarantees of the system, and it would be very interesting and more efficient to obtain some reasonable results, rather than considering a deterministic system, but exploring in a probabilistic way. Yes.
Yeah, I think indeed that one might bridge indeed falsification with other approaches in testing also that try to give you the confidence interval or the into the satisfaction of a specification and so on. And so, and then I was very curious about the combination of metaheuristics. Probably you can talk more about this. What is your strategy and so on? I've been using a lot simulated annealing, but I'm wondering, how can you actually combine them?
Yes. Okay, so let me, because I was too in a hurry to explain that. So basically is that you will have a number of solvers. So solver, when I say solver, that means that they call here metaheuristics or strategies like CMAES, simulated annealing, global nether-meets, and each method is good for some local region of the dynamics. It's very hard to know, to identify which one is good. In fact, we will use this coverage and robustness measure to exactly identify whether or not they are good. When we see that they perform poorly, then we will change. We will change the strategy using these two coverage, basically by when you see that it's stuck, or it doesn't improve the cost functions, and it doesn't explore widely. So using this detect blocking based on the coverage and the robustness, the current, the best robustness, then if it's no improvement of coverage and constant robustness for some period of time, then you switch And when you see that it's the local optima, then if you want to really get out, you try on the metaheuristic for the exploitation, it doesn't improve, then you will do the uniform sampling or like exploration. So you go to other regions of the state space. And so when you combine these methods, then you will see that here, if you just use them alone, then you obtain fairly good in the objective function, but it would take a lot of time to get into the good objective function. But if you combine them, and then you will detect quite rapidly that, okay, it's not worth exploring that region anymore. You just need to go away. Then you will see that here, for example, the number of functions, robustness function evaluation here, is you see that it's way smaller than what is needed for other metaheuristics. Yes.
Yeah, that's indeed very interesting. So you're using the geometry and yeah, this coverage measure to actually control, right, the sampling and so on,
Yes.
which tells how actually you can use indeed the logics and the robustness concept to have a sense of the geometry of the space in which you are working, and even decide on the fly. Right. Okay. So still asking the audience. Otherwise,
I have a
very good
question.
So
for the metaheuristics, are there any guarantees on the optimalities? Like,
okay, so the guarantees, theoretical guarantees, I think that you could see the very specific studies. For example, CMAES, there are a lot of studies, but for under very specific conditions. Like you will have, you will need to have a system satisfying some properties in terms of the dynamics in all the functions, objective function as well. It needs to be smooth, or you need to a lot of conditions. Then you will have a certain theoretical guarantees on the convergence. But they are active studies over this. But I mean that for the system, like cyber-physical system with a lot of switching, the dynamics are not continuous, not smooth, not non-convex.
It's basically black box for this research.
Yes.
So
and similarly, I think simulated annealing also has under some conditions also studies that show optimality and global optimum in due time, let's say after a certain amount of time or in probability.
Yes.
Good. So yeah, I think we are kind of about at the end of the slot. Just one very let's say more visionary or prospective questions on the future and so on. So definitely falsification is among the most used in industry, as you were saying, also methods and so on. Do you have any feeling right now on what kind of scale in general has been used to, or a more broader comment on the capabilities of formal methods so far, especially for hybrid systems in terms of size or applications, to give a broad idea of the state of the art?
Yeah, I think that I would say that you could handle a production model in, for example, Toyota, you could handle production models, which is, I think that very close to real life models. They are still research. I think that the models for research, but it's just the questions that you will need to deal with the you will need to have good simulator so that you will have good efficient simulations, and you will need to have people knowing the temporal logics, knowing time automata, formal methods to use. But I think that it will, if people are interested and interested in using and learning, I think that they are effective in improving the production time, the design time. Yes. In terms of, I think that, I cannot give the numbers like how many blocks in the Simulink models, but I would say that it's close to the production models. Possible.
Makes sense. That's great. And so if there are no other questions, are there other questions from the audience? Otherwise, I think we can say thank you again to Tao, and we are very happy to have you here, and don't want to also steal a lot of your time, as we know that it might be late in Europe. And so thanks again for joining us today, and to all of you, see you next time for the cyber physical system, and probably, hopefully, right, we could also host Tao in person whenever we start to travel again in the future, to have, if you ever come into the area, so please let us know. And there are chat. Thank you so much on the chat as well.
Thank you.
Thank you for the talk and the discussion, and see you soon, hopefully, to everyone.
Yes, see you soon, everyone. Yeah.